Okay, welcome back. Let's get started on Chapter 2 of the Baker text, Linear Programming, Allocation, Covering, and Blending Models. We're going to talk about the uses for linear programming. You're going to find that linear programming is really the most powerful application of the solver program. And you can do kind of classic transportation and distribution plot problems from supply chain management, production scheduling, whether to make or buy certain products in order to maximize profit, or what mix of make and buy, portfolio investment, when and how much to invest, procurement, staffing, and others. So, linear problems exhibit a specific type of form. And in fact, some of the work that goes into building models is to make sure that they follow the linear pattern so that we can use the linear solver because it is much more powerful than the nonlinear or the evolutionary algorithms also used by solver. So a linear problem has linear requirements for both the objective function and the constraints, and they must exhibit proportionality and additivity and divisibility, and we'll talk about each one. So let's talk about these in turn. Proportionality. The contribution from any given decision variable to the objective grows in proportion to its value. In other words, when any one decision variable doubles, for example, its contribution to the objective doubles. And of course, if you were to plot this, you would see a straight line. Additivity. The contribution from one decision is added to or possibly subtracted from the contributions of the other decisions. In this way, we can separate and identify the specific contribution from each decision variable. They are not muddled together, they are not multiples of each other. And then lastly, divisibility. Fractional decisions are fine. Okay. Now, this will cause sometimes a little bit of confusion when we get into things like chairs or tables, how many of certain things to make, and you end up with a fractional decision. But we'll discuss that when we get closer. So variables in a linear function always have an exponent of 1. They are never squared or anything like that. So for example, hearkening back to chapter 1 in our demand curve, okay, y equals demand, which equals 800 minus 5 times x. That is linear. Okay, everything has an exponent of 1. None of our variables, there's only one variable, so it is not multiplied by any other variable, so that one is fine. However, profit ends up with an xy, and then if you multiply it through, it ends up as x squared. Okay, so these two functions are not linear. Doesn't mean that they're not what they should be. Okay, but in this form, we could not use the linear solver engine to solve them. It would give us an error saying the linear assumptions are not valid. So the objective function. Let's take a look. Z equals CX1 plus CX2 and so on all the way up to however many variables that you have. So let's identify these. Z is the value of the objective. Okay, Z is often used as the letter designating the objective, but that's just a convention. It doesn't have to be that way. X are the decision variables, and the C values are the coefficients. Okay, and we'll use this in an example. Most of the math here, as I've already stated, most of the math in this course is really just algebra. Maybe a while since some of you have used algebra, but I'm sure it will come back. Let's talk about the constraints. Okay, constraints are typically three types: less than, greater than, or equals. All right. The left-hand side, and we designate that LHS, is a linear function. And I mentioned this in the last chapter that the left-hand side is usually some kind of a program, okay, or I'm sorry, a formula. The right hand side is usually a parameter of some type, designated by RHS. So, for example, you have a pencil plant, it makes red and yellow pencils, and it has a capacity of 10,000 pencils per month. All right, so we could make, for example, this is a feasible solution, 6,000 yellow pencils and 3,000 red pencils, okay? Because those are less than 10,000 total, okay? So this is a feasible solution. We don't know anything else about this particular example, so we don't know if this is an optimal solution, but it is feasible because it matches the constraint. Okay, the left hand side is a function, it's linear, and the right hand side is simply a parameter. So let's take a look at a linear model on a spreadsheet. Okay, and as I mentioned before, I'm going to be a stickler for form. All right, and this is the form. This is classic linear model form right here. And so this is brown furniture. At the top, we have the data. Okay, this is everything that we know about this problem. Okay, at least numerically. All right. So brown furniture makes chairs, desks, and tables. It has fabrication, assembly, and machining and wood constraints. We know the profit per unit, and we know the capacity for fabrication, assembly, machining, and wood. Okay. Our decisions are how many chairs, desks, and tables to make in order to maximize profit and stay within our constraints. Okay? Our objective is total profit, and our constraints are, and as you can see, what we've done is basically take these parameters right out of the data. Okay? And in fact, you don't even have to copy and paste them. You could just reference the cells if you wanted to. Okay? And so these constraints are they're labeled so that we know what we're constraining. Okay? We know that it's a capacity constraint. And so we will total these up, and I'll show you how to do that in a moment. The left-hand side is going to be a function. All of our capacity constraints are less than. And so, and the right-hand side are simply the parameters. And these can be copied and pasted right out of here or simply referenced. And so this is how your models, your at least your linear models should look. Okay, they can sometimes take different forms, and we'll talk about that. But for the most part, this is how they should look. The decisions should be in yellow. The objective should be in green. Everything should be labeled. And always reference cells when possible rather than embedding parameters or numbers into your equations. Sum product. Okay, this is going to be this is an Excel function. This is going to be a very important tool in linear programming. And basically, it's an incredibly powerful and time-saving tool within Excel. If you've never used it before, you're soon going to love it. Okay, produces the sum of the products of two or more cell arrays. These can be rows, they can be columns, or they can be whole matrices, so rows and columns together, as long as they are the same size. Okay, so row by row has to be the same size, column by column, or matrix by matrix has to be the same size. This is well suited to linear programming, and I'll show you that in a moment with the brown furniture example. So here we are again with brown furniture. Okay, and so how do we calculate, for example, our total profit? Well, our total profit is going to be a sum product function, and it is the array D10 to F10, which is right here, okay, times D7 times F7, which is our profit. Okay, so basically the numbers that go in here are going to be multiplied by the profit, and of course that will give you your total profit. And also, so the left hand side of the constraints will also use sum products. So, for example, the fabrication hours used will be that row array 462 times the number of chairs, desks, and tables. All right. And the solver will ensure that whatever decisions are made, that the total will be less than 2,000 hours. So we're going to talk about allocation models, the first set of models that we're going to use in linear programming. They are concerned with the allocation of finite resources. This is a very kind of classic problem in business. Everybody has finite resources. They can only go so far. So you want to allocate them wisely in order to maximize something or minimize something else. Okay. In this case, the objective is almost always maximization and usually of profit. Okay, so an allocation model is usually about maximization, and that means that the constraints are usually less than constraints based on resource capacities. Okay, that's what makes them finite, right? Is that we have capacity constraints. So, brown furniture, again, is a classic allocation model. We want to maximize profit based on less than constraints, okay? Because we have capacity issues, right? We have finite resources in terms of fabrication, assembly, machining, and wood. Okay, and so this data is going to come from different departments within the organization. They might be hard data, sometimes they might be estimates. So let's build the model, okay? First, we have to figure out what must be decided. That's not always easy. Remember, these come in the form of word problems with usually a data table attached. Okay, so what are we deciding? In this case, it's the product mix. How many chairs, how many desks, how many tables in order to maximize profit? Well, that's our next question. What are we trying to optimize? And in this case, it is the profit. It's the profit from chairs and desks and tables combined. So, what are we deciding? What are we trying to optimize? Essentially, what are we going to put in yellow? What are we going to put in green? And then finally, what are the constraints that we must consider? We have finite capacities of fabrication, assembly, and machining time, and a quantity of wood. So let's take a look at this algebraically, all right, as we continue to build the model. Sometimes this will help and sometimes it's not necessary. I don't always write out a model algebraically in order to solve it, and I don't always expect you to do it. Sometimes it helps, especially in some of the more complex models, okay, just to kind of get your head around what you're doing. All right. But anyway, we're going to let C equals chairs, D equals desks, and T equals tables. We want to maximize 16C plus 20D plus 14T. 16, 20, and 14, if you recall, are our profits per unit. Okay. And then we have constraints subject to 4, 6, and 2 times chairs, desks, and tables less than 2,000. These are the coefficients for your constraints. Okay, and so if you go back to the table, you'll see that these are the parameters that make up your capacity constraints. So this is the algebra, and as I said, you don't always you can sometimes bypass this, or basically you're doing it in your head, but sometimes it helps to write it out. Okay, so let's start building the model. Now, this is the same screen that I showed you a few slides back. All right. Notice also that the way we've laid this out, we have the data, decisions, objective, and the constraints. Notice also that we've lined things up. We try to line up in terms of columns the the constraints and their how they correspond to the decisions and to the data. It just makes it cleaner and easier Mathematically, it doesn't help you at all, but just in terms of understanding and interpretation, this is clean and a good way to do it. Okay, so this is the solver screen that we use as part of our model building, and our objective is C12. It is a maximum. We change the variable cells that are in yellow, and we add the constraints. And as you can see, the constraints can be added as an array rather than simply cell by cell, and that should save you a little bit of time. And for linear models, we use the simplex LP engine, if you will. And simplex is a linear programming algorithm. It's very powerful, and we want to use this as much as possible. It is guaranteed to find a global optimum, and it's much more powerful than the nonlinear or the evolutionary engine in solver. So linear programming is always going to be the preferred method. If you can modify the parameters of your program or your problem to create a linear model, that's always going to be preferable. And then of course you click solve and off we go. Okay, so here we have our solution. We came up with, or say we, the solver came up with 0 chairs, 160 desks, and 120 tables for a profit of $4,880. Okay. Notice also that two of our constraints, all of our constraints are met. Two of our constraints are equal. Left hand side and right hand side is equal, and these are known as hard or binding constraints. In other words, they're the real limiting factors for this problem. We'll talk more about that. So, the product mix problem is a variation of the allocation model, and there are added constraints, and these are often demand constraints. Okay, so let's go back to brown furniture, and we will say that we have a forecast now that we will sell 300 chairs, 120 desks, and 144 tables. And so on our algebraic model, this is pretty much the same, okay? But we've added these three constraints. Chairs less than or equal to 300, desks less than or equal to 120, and tables less than or equal to 144. This represents what we call a demand ceiling. Sometimes we have a demand floor. In other words, they would be this sign would be reversed. We'd say we want to sell at least 300 chairs, 120 desks, 144 tables. So you've got to take a look at how the problem is worded. Okay. In this case, it's a little bit ambiguous, but these represent demand ceilings, not floors. Therefore, they are less than or equal to. So let's take a look at our new spreadsheet. Everything else is pretty much the same, except we have our demand constraints now added to the spreadsheet. Okay, and it's typically we'll just put ones in each of the diagonal cells that correspond to chairs and desks and tables. Okay, and obviously what you will get when you do the sum product is that each one is less than or equal to 300, 120, and 144. So let's take a look at what this produces. Okay, so here is our solution. All right, and so we have 16 chairs, 120 desks, and 144 tables. Notice one thing: our total profit has gone down. Okay, and this is the rule with optimization. If you add more constraints, you will never get a better objective. Sometimes it won't go down, but the only direction it can go is down. You will never get a better outcome with more constraints. And so, as you can see, tables at the bottom is a hard constraint. We can't produce more than 144 tables, and so that limits our profit and reduces our profit. Okay, and that's going to be, you're going to find that holds true whenever we add constraints, is that the objective may stay the same, but most of the time it will go down. Now, let's introduce something called covering models, okay? And kind of the opposite of an allocation model, we want to minimize something. We want to minimize our objective, which is usually cost. And it uses mostly greater than constraints. And so here's an example of Herrick Foods. Then they make trail mix, okay? So you have the various components of the trail mix. All right, seeds, raisins, flakes, pecans, and walnuts. And you have in the grid the various vitamins, minerals, protein, calories, and cost for them. And you have a nutritional requirement on the right hand side. Okay, and so intuitively you should understand that we're going to want to meet or exceed the nutritional requirements while minimizing our costs. Okay, so the algebraic model is we want to minimize our objective. And so we have 4S, 5R, 3F, 7P plus 6W. Okay, and those are the costs of each of those components. We want to minimize that. And then we subject it to the nutritional requirements. And notice that the constraints are greater than constraints. Okay, so we want to add up the nutritional requirements or the nutritional impact of each of these components, and it's got to be greater than the right hand side. So our spreadsheet model looks like this. Okay, now as I said before, our decisions are laid out in a row. Okay, and that is typical. So here's our solution. All right. Notice we're not using any pecans or walnuts at all. They simply don't contribute enough to our model to warrant using. Okay, so if you really love pecans and walnuts, this answer isn't going to satisfy you. But in terms of the parameters that we set and the constraints that we set, we can satisfy the nutritional requirements and minimize our cost by using only seeds, raisins, and flakes. And notice that the units are fractional, okay, which is consistent with a linear model. Notice also that we have three hard constraints, okay? Minerals, protein, and calories are binding constraints. In other words, the left-hand side is equal to the right-hand side. So they represent the real limitations for this model. So if we wanted a different result, we would have to try to find a way of relaxing these constraints. So we've added some constraints here. Take a look at the model and see what's changed. Okay, you should notice that at the bottom we've added some constraints. So what have we done? We've essentially said that it's not acceptable for some of the products to be left out. I'm sorry, some of the ingredients to be left out. Okay, we have said that we need a minimum of 0.15 of every product in order to satisfy our constraints. In other words, we don't want to produce a product that doesn't have any pecans or walnuts. So we've set minimums on all of the ingredients. Okay, and so notice also then that our objective has gone up. All right, we're trying to minimize costs, so lower is better. But as I said, when you add constraints, your objective gets worse. In this case, since we're trying to minimize, it gets worse by going up. Our costs are higher. Let's take a look at a staff scheduling problem. Okay, Acme Communications wants to minimize the number of staff that they have working. And one of the constraints is that each worker works two consecutive shifts. Okay, so we have 6 shifts. We have various time periods for the shifts. All right, and they are concurrent, or they are consecutive rather. And then we have the staff requirements: 10 staff for shift one, 20 staff for shift two, and so on. Okay. And again, staff scheduling is a very kind of classic problem that we apply optimization methods to. So, our algebraic model, we want to minimize the number of staff. Okay. So, X1 through X6 is the number of staff for each shift, and then we we do the constraints. Okay, X1 plus X6 has to be greater than 10. All right, X1 plus X2 is greater than 20, and so on down our constraints. Okay, so we have to meet our minimum staffing, and we have to do so by shifting the number of staff in each period. Okay, so let's take a look at what it looks like in the spreadsheet. So this is our spreadsheet model with solution. Okay, notice everything is nicely lined up according to shift, lined up vertically. All right, our decisions are lined up and our constraints are lined up. Notice also at the bottom is that you have workers working 2 consecutive shifts. So you have for the 2 a.m. to 6 a.m. time slot, you have workers who have worked from 2 a.m. to 6 a.m. and workers who have worked 10 p.m. to 2 a.m. All right, add those up, and it has to equal at least 10. Back over here on the left, for the 6 a.m. to 10 a.m. slot, you have workers that started at 2 and workers that started at 6. Okay, and so you can see the pattern and how this works. And of course, on the right hand side are our staffing requirements, and this is just an inversion of these numbers up here. My mouse is a little sticky, so forgive me for that. Now, let's take a look at a shift variation. Okay, what's happening here is we have different shifts that start at 6, 7, 8, and 9. Okay, and these people will work an 8-hour day. All right, with an hour break in the middle. Okay, and that's why this looks the way it is, the way it does. Okay, so take a look at the constraints. We basically have starting at 6, working 4 hours, skipping an hour for lunch, and then working another 4 hours. Likewise, move over to the right, and this is the shift that starts at 7. Works 4 hours, skips an hour, and then works another 4 hours. Okay, so this is a bit more, the model is a bit larger. Okay, but we can still add these up. It's still basically the same form. The objective here is the author has just put ones here to do a sum product with the decisions. Honestly, the way I would do it, I wouldn't bother with that. I would just put a sum. This would just be a sum of these variables. Okay, but you can do it either way. And again, look at the spreadsheet models on the chapter spreadsheets and take a look at this. But try and see the pattern. Okay, especially for staff scheduling, if you can see the pattern, the problems become much easier to solve. Okay, so here is another variation on the staff scheduling problem. Okay, and what's happening here is that the staff can have a different lunch break. They can take a lunch break after 3 hours, after 4 hours, or after 5 hours. So as you can see, what we have to decide now is, for example, this column are the people that start at 6 and take lunch after 3 hours. These are the people that start at 6 and take lunch after 4 hours. These are the people that start lunch at 6, start the shift at 6 and take lunch after 5 hours. So because we have three different possible lunch hours, we have to kind of triple our decisions. Okay, and so look at the constraints at the bottom here. We have 3 hours, an hour for lunch, and then 5 hours. Over to the right, we have 4 hours, an hour for lunch, and then 4 hours. Okay, and so again, see the pattern. All right, once you see the pattern, you can build a model like this very quickly. And our objective is 54. Okay, and again, that's a sum product of these ones times this, but I would just do it as a sum of the decision variables. The last type of model that we're going to look at is a blending model. Okay, so let's take a look at Brown Furniture again. Okay, and this is pretty much the same screen that we had before, and that is we have our constraints, we have our decisions, and we have our capacity constraints and our demand constraints. So this model is the same as the one that had the demand ceilings. Okay, and so we're going to work off of this. All right, and remember that our decisions were 16 chairs, 120 desks, and 144 tables. Okay, so now we want to add a different type of requirement. Okay, this might come from marketing or somebody higher up. And the new requirement is that each product type produced must be at least 20% of the total product mix. Okay, so what does that mean? For example, so for chairs, C over the total, C plus D plus T, is got to be greater than or equal to 0.2. All right. So that's an easy enough constraint to understand. All right. The percentage of chairs has got to be greater than or equal to 20%. Okay. The problem is this isn't linear. Okay. So this is not going to work with the linear solver, which is what we want to stick to because it's the most powerful. So we're going to have to play around with this a little bit. So then what we do is we move C plus D plus T over to the right hand side through multiplication. All right. And then we multiply that 0.2 through. So we have C greater than or equal to 0.2C plus 0.2D plus 0.2T. Okay. Now, what we want to do here is now move all of those that formula over to the left hand side and just leave a 0 on the right hand side. Okay, because remember for our model we like to have formulas on the left and parameters on the right. Okay, so we simply subtract everything on the right hand side from both sides, and we end up with 0.8C minus 0.2D minus 0.2T greater than or equal to 0. All right. The same thing is going to apply for desks. All right. You just do the algebra. You'll see this works out just like this. And then finally for tables. Okay. And again, I encourage you, this is for blending models. It really does help to work through the algebra before you start doing the spreadsheet model. Now, as I said, I don't always do the algebra right at first for a lot of these types of problems, but for the blending models, it really does help. So here is our model and our solution. Okay, so we still have our capacity constraints. All right, here we still have our demand ceiling. We left that in. Okay, and now we have our blending constraints. And as you can see, these values here correspond to the algebra that we just worked out on the previous slide, and they are all greater than or equal to 0. Okay, so what we've done is taken a non-linear constraint and made it linear. Okay, and now we can take advantage of the power of the linear solver, and you have our solution and our total profit. Here's another blending model, Keo coffee roasters. All right. And so we have different kinds of beans, all right, and they have different characteristics for aroma, strength, and we have a supply and a cost per pound, all right. And our minimum output is 4,000 pounds, so we need to produce at least 4,000 pounds. Okay. Now here we're not doing percentages, okay? We're just dealing in real numbers. And so, what we do for blending constraints in this case is we subtract the target from the actual. Okay, so for example, for aroma, our target is 78. Okay, and so we subtract 78 from 75, from 60, and from 85. You can see it up here. Okay, so that gives us -3, -18, +7. And again, as we do with blending constraints, it is greater than or equal to 0. For strength, 16 is our target. Okay, so we subtract 16 from 15, from 20, and from 18, and the result is -1, +4, +2, and then that's greater than 0. So these are actually a little bit easier than the percentage ones. Okay, and you could actually work this out as a percentage also, but this is just easier. And here we have our spreadsheet model and our solution. Okay, so our blending constraints are right here. Our total output is right here. So the combination of Brazilian, Colombian, and Peruvian has to be at least 4,000. And we also have our capacity constraints. Okay, our supply of Brazilian is only 1,500, so what we produce has got to be less than or equal to 1,500. For Colombian, it's less than or equal to 1,200, and for Peruvian, it's less than or equal to 2,000. And as you can see, Brazilian is a hard constraint. Our total output is a hard constraint, and our aroma is a hard constraint. Okay, so we need to, if we wanted to reduce our cost even more, we would have to relax some of those hard constraints a little bit. And that's it. This is actually a lot. There was a lot. We covered a lot of different models here: allocation, covering, blending, and hybrid. Okay. And so I would encourage you to go back over this and look at the spreadsheet, the chapter spreadsheets, and kind of work through this, because a lot of what we will do from here on out is usually one of these models or a variation of these models. Okay. And so it helps to classify the problems in your mind so that you know what you're dealing with. In terms of troubleshooting, you're always going to run into problems with these, especially at first. Some things, and I'll demonstrate these things when we have our in-person sessions. But some of the things that you can do to troubleshoot. One thing is Control tilde. When you're in Excel, if you hit Control tilde, it will show all the formulas. Okay, and that can help. You can also use the trace precedence function in Excel, and it basically will take a formula and tell you what cells are feeding that formula. You also check your data. Sometimes it doesn't hurt to put some dummy parameters or dummy data in the yellow cells just to ensure that your calculations look right. Also check your constraint directions. All right. Make sure that your less than should be less than and your greater than should be greater than. Okay. And again, this is especially important when you're dealing with demand, because demand can sometimes be a floor or a ceiling. And so it's not always real clear from the wording of the problem. So make sure that you double check that. Otherwise, that's it. And I'll see you again when we start on chapter 3.